All right, let's formally introduce what induction looks like and do an actual example of proving something by induction. So we were working with a lot more concrete of things. So here's what weak form induction is. And there's two kinds of induction. If one of them is weak form, what do you think the other one is? Of course, probably strong form. But weak form is already pretty strong. And honestly, this is kind of the default as for what I've seen. This is kind of like our standard induction. This is what I've used the most in my own history as well. So this is what it looks for. So it starts with something called the base case. And that says, and remember what's the format that we can use induction on? The format that we can use induction on is some kind of predicate about some natural numbers. So if we know that the predicate for some number is true, and that's for some natural number. So it could include 0. Here's some a shorthand that's sometimes used, an integer that's at least 0. Just this is a non-negative integer, 0 or bigger. Okay, probably doesn't matter to you guys as much as it matters to me, but I'd like to get it right. Okay, and this next step is maybe a little bit more confusing. And predicate for any x implies that predicate for the next one. And this has got to be true for any x. Okay? So this is going to be for any x bigger than little x. Bigger than, yeah, specific. Yeah, it's like any x. So this first step, well, hold on, let's give you the conclusion. I don't want to keep you. Then what we know is that pred x is true for all x bigger than or equal to x naught. Okay, so some terminology, and maybe before terminology, we'll just logically say what this is talking about. This is saying, right, let's show it for 1. And then if this implication holds, if the implication that it holds for some number always means that it holds for the next number, then we combine these two things to say, okay, well, it's true for every number that's at least that first one. So again, I said this is called the base case. This is called the inductive step. Can we always show it's true for the next one? And then specifically this part right here is called the inductive hypothesis. It's something that we're assuming. To show implication, oops, I wrote hypotheses. To show implication, to show an if-then, we assume the if and we show the then. We'll get some practice with that. So to put this induction little outline into a picture, it's like dominoes. Our base case is the first domino. Let's show that the first domino is falling. And then the inductive step is saying, if we choose any domino, if that domino falls, will the next one fall? And if that's the case, we can combine those two things to say all the dominoes are falling. Now, it's very important that our inductive step is for any arbitrary domino. It's for any arbitrary n. Right? Because it can be true for almost any domino. But if there's a pair of dominoes that it's not true for, well, then it's not going to hold. Right? This domino is not falling down. Okay? That's some Photoshop by me, by the way. Made this. I couldn't actually find a picture with a missing domino. Anyway, so again, that's what we're going to do. That's what the base case is. Base case is we'll show it for the first one. Inductive step will say if it's true for anything, will it always be true for the next thing? We'll combine those two pieces of logic to get a row of falling dominoes, no gaps. So let's look at what this looks like. And we're going to do it with a binary tree, just like we did before. So we're going to prove C from earlier. All right. And that was the question about binary trees. I'll just show it real quick. Right here. The number of leaves in a binary tree is one more than the number of internal nodes in that tree. And luckily for us, we already set it up. We're saying P of n is going to be the proposition that this statement is true for a binary tree of height n. Okay, so what does our base case look like? And maybe before base case, let's just include some variables. So, right, n is going to be our height. Let's say the number of leaves in a tree of height n is L sub n. So, number of leaves in tree of height n, we're going to need that. And what are we trying to show? That the number of leaves is one more than the number of internal nodes. So you can use I sub n for the number of internal nodes. Again, in trees of height n. You could use other variables. You might be bothered, say, Jason, why are you using a capital L and a lowercase n? That's because I think lowercase l's look too similar to lowercase i's. But I also don't like capital I's. So you can do what you want. And I'll do what I want. All right? That's the cool thing about variables. You can make them any letter you want. Okay? So we need to prove this for a base case. So that's super easy a lot of the times. Okay? Can we show that this is true for some tree? And I'm going to choose the smallest possible because I want this to be really powerful. Right? We're showing, if we want to prove for everything at least something, our base case should be a small something. So a lot of times we treat this as like 0 if we can. So let's look at a tree of height 0. Binary tree of height 0. Well, is that true? What does a binary tree of height 0 look like? Looks like that. Well, how many leaves are there? 1. How many internal nodes are there for height 0? None. There are no internal nodes. The root is a leaf. So, we want to show, right? What did we want to show? We wanted to show that the number of leaves is one more than the internal nodes. We wanted to show this for any n. We're starting with the base case, which is n equals 0. Did we show it? Yeah. Heck yes, we did. Right? L0 is I0 plus 1. Check. Base case is shown. Now, that's a lot of times going to be pretty simple. Can we show it for one case? Yes, a lot of times very easy to show it for one situation. Now what we have to do is the more complicated step. It's the inductive step. Can we show that pred x implies pred x plus 1? All right, so that's what's next. Inductive step. That P of n implies P of n plus 1. So how we do that is we start with the inductive hypothesis. Inductive hypothesis is assuming the premise, right? In order to show an implication, you have to say, if this is true, then that is true. So if P of n is not true, then this is true by default. So the only interesting part is when our premise is satisfied. Remember how implications are true. The only way they can be false is if true and false. So to prove it, all we have to do is that if this is true, then the other thing's true. Okay, so assume P of n. Assume a tree of height n has one more leaf than it has internal nodes. So again, let's say we have, so we know that we have some tree, right? And I don't know how big this tree is. We have some tree of height n. Is it going to be true when we add another layer, right? So if we add another layer, are we going to have the things that we want? This will be n plus 1. That's what induction's all about. We'll do the base case. We'll assume it's true for some n, and we'll try to show it's true for the next one. All right, because then we get that implication. And then if this is true, right, and we know it for 0, we use this to show it's true for 1. We use this to show it's true for 2. We use this to show it's true for 3, et cetera, till we get it's true for all heights. Okay, so let's try to find what is I of n plus 1. What is L of n plus 1? We need to find those out. And this picture really helps us here. And again, in this picture, I do have a certain height, but it doesn't really matter because this picture helps us see what's going on. How many internal nodes are there for a tree of height n plus 1? Well, notice that the entire previous tree is now all of our internal nodes. All right. So there's a few ways about doing this, and I actually didn't think about which way I wanted to do this, so I'm going to choose one way, and we'll see how it goes. Maybe let's. Yeah, I'm actually not exactly sure which way I want to go on this one. Let's start with the new leaves, actually. So the new leaves, right, is always just going to be some power of 2, right? 2 to the 0, 2 to the 1, 2 to the n, 2 to the n plus 1. It's essentially 2 times the number of leaves that we had before, right? If we think about all of these new leaves, it's just going to be double the leaves that we had before because it's a perfect tree, right? If it wasn't a perfect binary tree, then we wouldn't have this. But because we have it, we know this is the case. And that's kind of a general strategy for induction. And like, it's just when you're doing this stuff, try to put it in terms of the previous one, because that's what we're assuming. We're assuming it's true for the previous, right? What was P of n? Right? P of n was the proposition that L sub n was equal to I sub n plus 1. We can use this. We're assuming it. All right. So now what is I sub n plus 1? Because again, this is blue is what we're assuming, and we want to show it for the next one. We want P of n plus 1, which is we want this. And that's why we're trying to find what L sub n plus 1 and I sub n plus 1 are. Because we know blue, we're assuming blue to be true. We're saying, does blue mean green? So we need to kind of figure out, well, what is the number of internal nodes now? And the number of internal nodes, right, was the number of internal nodes that we had before plus the leaves that we had before, right? Internal nodes is all the whites in this picture. And that was all of the internal nodes from before plus all the leaves from before. And again, it's very helpful to write things in terms of before because that's what we have. So now let's look at this. All right. So we want this green thing to be true. And let's look at the right-hand side. What is the right-hand side of this green thing? It's I sub n plus 1 plus 1. I sub n plus 1 is this. Right? The right-hand side is this. I sub n plus 1 is just this. And then we're adding the 1 just like we did before. Now we want to prove that this is equal to L sub n plus 1. How are we going to get there? And so there's a couple of ways that you can use that information, right? You could solve for L sub n and substitute this over here. But we also know that we eventually want to use this inductive hypothesis, right? We're always going to need the blue thing. We're always going to need the inductive hypothesis, which is, why we assumed it. We needed to assume it. So let's actually use it right now. We have an L sub n, right? And we know L sub n is I sub n plus 1. So that gives us I sub n plus L sub n. L sub n is I sub n plus 1. And then we still have this plus 1 that was left over. Now, what do we have? This is pretty neat. I'm going to actually bring us over to the next page. But what we have, if we simplify, is 2 times I sub n plus 2, which is 2 times I sub n plus 1. If we factor it, what is I sub n plus 1? I may have gone, wait, I think I went in the wrong direction. This is okay. This is okay. This is showing a good thing that sometimes happens in proofs. Sometimes you do proofs and you take more steps than you need to get there. Because we're going to use this again, right? I sub n plus 1 is L sub n. I did a little circle, but that's okay. Why is this good? All right. 2 times L sub n was L sub n plus 1. We wanted to show this green thing. We wanted to show that L sub n plus 1 was equal to I sub n plus 1 plus 1. We did it. We started with the right-hand side. We showed through a few steps. So we went to the other side. And I'm joking, right? Because I'm a little embarrassed that I did this. But I really, really want to hone this in. When you're doing proofs, you're not always going to do the right thing at the right time. Sometimes you're going to prove something and it'll be a totally valid proof. This is a totally valid proof, but you'll take more steps than you need to get there. It's kind of like coding in a way, right? It's like if you always worry about finding the best way of coding something at the very start, sometimes, right, you're going to get like analysis paralysis and you're not going to be able to go. So for proofs especially, and I'm not a coding expert, so maybe this doesn't apply to coding. For proofs especially, sometimes just write things down. Sometimes play with this. And then, yeah, if it was important that I had a really good looking proof, I would go back and edit this a little bit. And to be very clear, the point I'm saying is I made this substitution when I really wanted things to be in terms of L. So I had to substitute it back later. Okay, so my proof took a couple steps more than it needed to for that inductive step. So I just really do want to really drive that in, right? It's okay to not do things like the best way. And yeah, I could go back and fix this, but I think it's nice to show that it doesn't always have to be the smoothest way. Just kind of work through things until you get there. So what have we done? We've shown the base case was true. We've shown it's true for a tree of height 0. We've also said if it's true for any random height, and that's a big if. If it's true for any random height, it's always going to be true for the next height. That's what we showed right here in this green step. So we can say by induction, P of n is true for all n greater than or equal to 0. All right, we have shown that this is always true for a binary tree of any height, which is really powerful. So pretty complicated proofs, pretty hard proofs, but again, what were the main steps that we did? We're going to do more examples showing this inductive step because that's the harder part, right? That's assuming it's true for something, and we're going to have to use that something to show it's true for the next one. That's really the core. And there's like a lot of proof strategies that you may have done in other math classes. I think everyone here has probably taken some kind of trigonometry. If you remember trigonometric proofs, a lot of this stuff is the same. If you want to prove an equation, you start with one side of the equation, you try to get to the other side of the equation. We're always going to be trying to figure out how we can use this. We're always going to try to look at where we're going. All right. Let me know if you have any questions. We'll do more examples in the next video.